Okay, this is section 5.6, standard enthalpies of formation. I put the symbol for it just to the right. Delta H sub F with a degree sign. Okay, so that's a little degree sign. Let me actually make that a little bit clearer for you so you can see. There you go, a little degree sign there. So standard enthalpies of formation are there to help us do calculations. Essentially what's done is certain materials are given the value of 0 for their enthalpy values. So for example, we would say that oxygen, the most stable form of oxygen at room temperature, is oxygen gas. Now there are other forms of oxygen out there. So for example, there's ozone. This is called ozone, O3. It's less stable than O2. It's pretty reactive actually, but it does exist. And then there's atomic oxygen as well. This is atomic, it's not molecular. And this one is even less stable, very unstable. It's very reactive. It will combine with other atoms, okay? So what we do is we say the following. We're going to give quantity of delta H of formations 0 to certain quantities, to certain materials. So for example, this one right here is given the value of 0, okay? Another example would be H2. This one's given arbitrarily, really, the value of 0. So what is the standard enthalpy of formation? Essentially, it's this following idea. Imagine that we're going to make a mole of carbon dioxide from the elements that comprise it. So we're going to take carbon, and we're going to take oxygen, and we're going to form carbon dioxide. And we're going to do this at 25 degrees C, okay? All right, if we do that and we measure delta H, so this is done experimentally, we're going to call this delta HF with a degree sign, delta HF naught. And we're going to measure it. And if we did, we would find that it comes out to minus 393.5 kilojoules per mole of CO2. In other words, if you took carbon in the form of graphite, which is the most stable form of carbon, and 1 mole of molecular oxygen, O2, which is the most stable form of O2, and at room temperature, you ran the reaction, you measured how much heat was released. Notice it's negative, so that means the heat's released. You would get this value, 393.5. So what we're going to do is we're going to make a table. We're going to say, okay, making 1 mole of this compound from the elements, the most stable elements that are in it, we're going to measure what delta H is, and we're going to put that in a table. And if we do the same thing, for example, if we take a mole of hydrogen and half a mole of oxygen, and again at 25 degrees C, we measure what delta H is to make liquid water. We're going to call that the standard enthalpy of formation. Standard is that degree sign, so that's standard. The F is formation. And what we would find is it's minus 285.8 kilojoules per mole. And we just keep doing this for many, many different substances. We measure the delta H of formation, the amount of enthalpy associated with making a mole of that particular substance from its elements, and we make a table out of it. Here's another one. Graphite plus 2 moles of hydrogen We're going to keep doing it at the same temperature because it turns out that it depends on the temperature. So we want to make sure everything's done at the same temperature. And we make a mole of this substance right here called methane. And we measure delta H for it. And you get these values here, okay? And these are called standard enthalpies of formation. Formation because you're making a mole of them. Standard because they're done under certain conditions. And the conditions they're being done in is that the substances that you're making are in the state of matter that you would expect them to be at that given temperature, as are the reactants. So in other words, we're not going to use liquid oxygen to do this, and we're not going to form solid carbon dioxide. We're going to form the states that these materials would be in at 25 degrees C. So those are standard conditions, okay? So now, let me make just a small, this is just a small table. Based on what we have here. So here's our material. And then here's our delta H of formation under standard conditions. And I'm going to put the units up here. So that way we don't have to write it for every material. Kilojoules per mole. Okay, remember a kilojoule is 1,000 joules. So we have a few already, right? We have oxygen gas. We already said that we're going to define that one as 0. And that hydrogen gas, we're going to define that as 0. And if we have graphite, we're going to define that as 0. So some materials just are given the values of 0. Other materials, that's an S by the way, other materials are measured. So for example, carbon dioxide, we would measure this and it's minus 393.5. And liquid water, minus 285.8. And it turns out, oops, H2O, that the state of matter is actually important. So making a mole of gaseous water at the same temperature gives us a different value. Negative 241.8. Okay, so the state of matter is important here. And then methane in the gaseous form, minus 74.85. And we could just keep doing this for many, many, many different materials. Okay? In fact, you can even do it for atomic oxygen. And it's plus 495. Okay? So we can tabulate these, and they're all shown in your textbook. In the eBook, they're shown in Appendix 2. So you can click on the little link that says Appendix 2, and it will give you the heat of formation. It's done alphabetically based on element, and the organic substances are down at the end, so they're separate. So if you're looking for methane, for example, you won't find it under carbon, you'll find it under the organic substances. That's a separate table, and they're all shown in there. Now, you might ask, okay, that's fine, we have these enthalpies of formation, which is essentially how much enthalpy change there is for making a mole of this substance. Okay? What use is that to us? How can we use it? And it turns out there's a very practical use for this. So I'm going to erase all this, but I'm going to show you the practical use of it. The practical use is this. Suppose I run a reaction. And the reaction I'm going to show you as an example is the combustion of methane. This is a 2, by the way. Okay, so we're going to combust methane with oxygen, of course, to form carbon dioxide and water. And we want to know what delta H of the reaction is under standard conditions. We want to know what that is. Well, there's a couple of different ways we could figure it out. What we could do is we could use Hess's law, and that's essentially what we're going to do. we're going to use the standard enthalpies of formation to calculate delta H of reaction under standard conditions for this particular example. So here's how we go about it. What we do is we go to that Appendix 2 or to some table, and you look up the values of their heats of formation. So I'm rewriting these ones that we just had a little bit earlier. Right? These are all in kilojoules per mole, right? And those are the standard enthalpies of formation or standard heats of formation. We often say heats instead of enthalpy because, oh my goodness, it's a long word, enthalpy. So why not just say heat? Because remember, at constant pressure, the heat of a reaction is equal to delta H, right? So the enthalpy change is equal to heat under constant pressure. So let's go ahead and use that. So now here's what we're going to do. I'm going to give you a little formula, and I'm going to show it. It's a little different from your textbook here. It's essentially this. Delta H of reaction under standard conditions. And I'm going to use the symbol for the sum. This is a mathematical symbol, sigma. The sum, meaning we're going to add up the heat of formation of all the products times the number of moles of that given product. And then we're going to subtract from that the sum, adding all up, the heat of formation of every reactant, again under standard conditions, times the number of moles of each reactant. Okay? So there's our little mathematical equation. It's shown a little bit differently in your textbook. Equation 5.18 and equation 5.19. This is the more general way that this equation is shown. Now, let me show you how we do this. What this says is, you take the heat of formation of the first product and multiply it by the number of moles of the first product. So our first product is CO2. We have delta H for it, and the number of moles is 1. The coefficient is a 1. So I'm going to write it this way. Minus 393.5 times 1. So I'm taking the delta H that I looked up in Appendix 2 and multiplying that by the coefficient in front of that particular substance. Then I'm going to add to that the second product. The second product is right here, water. So minus 285.8 times 2, right? Where's the 2 come from? Right here. Now I'm going to put this in brackets, just so that you can see that you're adding those two terms together. Now we're going to subtract the same thing for the reactant. So let me put another bracket here. So the first reactant is methane. The coefficient is a 1. So minus 74.85 times 1 plus, sum means add. So you're adding the products and then you're adding the reactants. So plus the second reactant is 0, right? We said that some materials have this value of 0 times the number of moles, which is a 2. Okay? Now, if we go ahead and calculate this out, you're going to add up the products first. So be careful. There are signs in here. Sometimes they're positive, sometimes they're negative. More generally, they're going to be negative. So negative 393.5 plus 2 times negative 285.8 is negative 965.1. I'll go ahead and put the units in here, kilojoules per mole. So I'll put that in the brackets again, just so that you can see that what I'm writing there is everything that's on that bracket on the left. And then we'll do everything on the right. So now you're going to subtract the reactants. Now the reactants are easy because, right, because it's negative 74.85 times 1. But then the other term is 0, 0 times 2, right? So you get negative 74.85 kilojoules per mole. Okay? So now, if you're subtracting a negative, that's like adding a positive, right? So you get negative 965.1 kilojoules per mole plus 74.85 kilojoules per mole. Okay? And so it looks like it comes out to negative 890.25. So I'm just going to round that to 2 kilojoules per mole. And that's our delta H of reaction under standard conditions. Okay, so let's review that equation. The equation says that if you have, when I say equation, I mean this one right here. When you have a reaction, you want to know what delta H for that reaction is. We call that the heat of reaction. Okay, heat of reaction. The way you calculate, or one way to calculate, it's not the only way, one way is to go to the appendix or go to some table and look up the heat of formation values for every substance in the equation. And if you can find all of them, you can use this equation. So you look those 4 values up. By the way, elements like oxygen that are in their most standard state, they are usually 0. So hydrogen, H2 is 0, O2 is 0. Then what you do is use this equation. You take the heat of formation that you've looked up, multiply that by the number of moles in the balanced equation for that substance, add it up for all the products, add it up for all the reactants, and then take the difference. And just be careful of your signs and you work through there. So this would be the heat of reaction for the combustion of methane, 1 mole of methane. And you might ask, well, wait a minute, what if I balanced the equation differently? What if I balanced it and I said, hey, I'm going to have 2 moles of methane and 4 moles of oxygen and 2 moles of carbon dioxide and 4 moles of water? Wouldn't that change the value? And that answer is absolutely, it would change the value. It would change the value. If you multiplied the whole equation by 2, then that would change your value by 2 as well. But that's perfectly fine if we know what we're, for what the equation looks like, we know what we're calculating. Okay? So you can practice a couple of these, a bunch of them in the textbook, and I'll go over at least one of them in a separate problem. Standard enthalpies of formation or standard heat of formation.